Hello students, in this lecture we will be studying the stability of a control system. Now stability is an important aspect of a control system in analysis and in designing of a controller. Now for a dynamic system is considered to be a stable if the system is BIBO in nature. BIBO means for bounded input there is bounded output. That is referred to as a BIBO system. A dynamic system of such systems are stable. Now we know that all the forcing functions so far which we have studied, that is step or pulse or sinusoidal, they all are basically your bounded systems, bounded inputs. Basically they all are bounded inputs, and for the output to these, they are also of bounded output nature. Clear? So practically unbounded outputs do not exist because all physical quantities are in their limits. So unbounded normally exists in theory. Now a system with a response something like this, something like, let's say this is the steady state value, and if the system is behaving like this, something like given by this thing or something like this, these systems A, B or C, they are classified as stable systems. Whereas a system something like these, time and we have response. Similarly over here the x's were time and response. A system whose behavior is something like this, whose amplitude increases with increasing time, or which shows a behavior something like this, or which shows behavior something like this. All these systems A dash, B dash or C dash, they are termed as unstable systems because with respect to time they are not able to achieve a steady state value or a limiting value. So with time their amplitudes, their outputs, their response goes on increasing, so they becomes unstable. Whereas for stable systems, the output of the response achieves a steady state or a constant value. That are stable systems. Now suppose we have a control system something like this. Let's say this is G1, we have G2, let's say we have U, we have G3, C, that is R, and negative feedback system, and let's say the measuring element is by H. Okay, it is H. Now sorry, for these systems if we calculate C by R, so C by R is nothing but the product of G1, G2, G3 over 1 plus G1, G2, G3, H. And if we calculate C by U, it will be nothing but it will be G3 upon 1 plus G1, G2, G3, H. Or combiningly or collectively it can be written as G1, G2, G3 upon 1 plus G1, G2, G3, H times R plus G3 upon 1 plus G1, G2, G3, H times U. So that is for the entire system in terms of your set point value and in terms of the load. Now if you see clearly in both these terms, the denominator part, specifically the denominator part. So if we look at this thing, the denominator part in both the terms is same, irrespective of whether we are taking C by U or we are taking C by R, whether we are dealing with the server problem or we are dealing with the regulatory problem. Irrespective of these cases, the denominator in both the terms for the closed system is almost same. Clear? Now I'll come to this thing later on. Now suppose this my closed system becomes open system. That means there is no feedback going back. So what will be the overall open loop transfer function? Overall open loop transfer function, that will be nothing but there will be the product of G1, G2, G3 and H. So let's say G open loop transfer function will be nothing but G1, G2, G3H, because all the blocks are in series, so they get multiplied. Clear? Now if you see, if we are dealing with the open loop transfer function, it's nothing but the product of all the blocks. And if you look at the transfer function of the closed system, the denominator part, look at this, it is 1 plus G1, G2, G3, Gh. So that means we can say that for overall, not overall, closed loop transfer function will be whatever the terms in the numerator, but in the denominator it's always 1 plus G open loop transfer function. Yes or no? If you look at either C by R or C by U, the denominator is same, and what is the denominator? It is 1 plus G1, G2, G3H. And what is G1, G2, G3H? It is nothing but it's the open loop transfer function. So instead of writing this entire expression, can I write directly 1 plus G open loop transfer function? Clear? Now for closed loop systems, whether it is C by R or whether it's C by U, the denominator term, the denominator equation is known as characteristic equation. It's very important. It's known as characteristic equation. So if anybody asks you what is the characteristic equation is nothing, you multiply all the blocks and add 1. So it is 1 plus G open loop transfer function equal to 0. So this is the characteristic equation of the control system. Clear? Now characteristic equation we know, so it is nothing but it's the product of G1, G2, G3, H equal to 0. Now if we put the transfer function values, let's say G1 is 1 upon tau 1s plus 1, G2 is 1 upon tau 2s plus 1, it can be anything, it can be second order, let's write tau 3s plus 1, Meyering element, again dynamic lag, so 1 over tau ms plus 1. So all these they get multiplied, and what do we have? We have nothing but a polynomial equation in terms of what? S. Clear? We have a polynomial equation in terms of S. So can I say that that polynomial equation can be something like a naught S4 plus A1 S3 plus so on, with a constant something like m at the end? Clear? Because if you multiply this transfer function with this and with this, so what do you get? You're gonna get a polynomial equation in terms of S. And let's say this is the that polynomial equation. Now can I find the roots of this polynomial equation? Roots, let's say the roots are something like R1, R2, R3 and so on. Clear? So depending upon the roots of the characteristic equation, depending upon, I again repeat, depending upon the roots of the characteristic equation, we can identify whether the given system is stable or unstable. So we have characteristic equation, that is this thing. We find it out the roots of the characteristic equation, because our characteristic equation is a polynomial term. We find out the roots, then roots can decide whether the given system will be stable or unstable. How? Let's suppose let us suppose that S1, S2, S3, S4, S5 and S6 are the roots of characteristic equation, that is 1 plus g equal to 0, 1 plus g is equal to 0, where g is nothing but the product of g1, g2, g3 and h. Clear? Now these roots are there. Now what we do is, let's plot a plane. In the plane, with these are your real axis and these are your imaginary axis. Let's try to place these roots, all 6 roots, in this plane of a complex number. Now suppose one root is somewhere here, S1. The other root is somewhere here, that is S2. Let's say third root is somewhere here, that is S3. Okay, this is, if this is S2, let's say this is S2 star. If this is S3, let's say this is S3 star. Next root S4, and let's say this is S4 star. Let's say fifth root is somewhere here, somewhere here, the fifth root S5, and then we have the sixth root, that is S6. Clear? So what we have done is, we have simply placed or located the roots in the S plane. Now if suppose any root is having any polynomial equation, characteristic equation is having roots similar to S, that is, it is having constant a1 with imaginary part 0. So such roots will give an expression in the response something like this. So this term will be there in the response of that particular system if we have roots similar to minus a1 naught. Number 2, now suppose if the roots are conjugate in pair, and represented by S2, that is, it's minus a2 b1 or minus a2 minus b2. If suppose these are the roots of S2, now for such roots the response will be having these terms in its numerator, in its response, that is c1 cos of beta 2t plus c2 sine of beta 2t. These terms will be there if the polynomial equation is of nature S2. Now if the polynomial is of nature S3, then the nature of response will be something like c1 cos of beta 3t plus C2 sine of B3t, something like this, because obviously we have the roots are 0 and plus 3, 0 and minus B3. Clearly? Further, now if the roots are of nature S4, that is plus minus A3 into B, sorry, it's not plus minus, my mistake, it's A3 into comma plus minus B3, and for such roots the response nature is of e raised to power a4t, it's 4 basically, e4t into c1 of cos of bt plus sine of bt. Let's just think. Now if the roots are of nature S6, that means A5 0, if the roots are of nature S6, then the nature of response is this C1 e raised to power A5t, and if the roots are of nature S6, that is S5 right, at the center, so at the center both the terms are 0, so it's nothing but it's some value, some constant. Clear? So depending upon the roots of the characteristic equation, we can identify whether the given root will be S1, S2, S3, S4, S5, S6 or S7. Now there are different methods to find out the stability of a control system. We'll be remembering this thing because we'll be using this particular graph somewhere else later on. So now in order to determine the stability of a system, there are different rules or different methodologies which we will be following. First is your Routh test. Second is your root locus, followed by frequency response, and the next is your Bode diagram. Clear? Now why they've written specifically in this order, because you know the easiest of all is your Routh test, but there are certain limitations to Routh test which will be eliminated, will be root locus. Further, there are some certain limitations of root locus which are solved by the emergency frequency response, and still after having this response, frequency response, there are certain results which are not verified. They are called as Bode diagrams. So let's start with your first test, that is Routh test. Routh test. Now it's a pure algebraic method having positive real part, but from this we can only determine whether the given system is stable or unstable. Clear? So let's study first Routh test. The limitations and the advantage, disadvantage I'm gonna tell you later on, but for the time being, remember this thing. We're gonna write a polynomial equation using standard equation of higher order. Like for example, suppose our characteristic equation is something like this: a naught Sn plus a1 Sn minus 1 plus a2 Sn minus 3 plus so on. Once we prepare the polynomial equation, we're gonna write it down in the descending order of S. Once this is done, we're gonna prepare an array, and based upon the results of the array, we can finally say whether the given test is for stable systems or unstable systems. Now for the table, let me take an example. Suppose I have a characteristic equation of a polynomial function as below, that is a naught S7 plus a1 S6 plus a2 S5 plus a3 S4 plus so on, and we have a7 equal to 0. Now we're going to prepare an array to solve this thing. Now remember, in an array, that will be first entry, second entry, third entry, and so on. Then the first entries we're going to write starting with this coefficient with the highest power. What is the coefficient of this? This is a naught. We're going to leave the another, move to another, a5, a2 S5. So we have another a2 S5, and then so on. We're going to have a2 a3 a4 can be there, and then so on. Rest, the ones which are left over, they're going to come in the second array, a1 a3 and then a2. We're going to leave it a2 as it is. Okay, now moving further, now we're going to have b1 b2, we're going to have c1 c2, we're going to have d1 d2, we're going to have e, so on. Now where to stop? Now in Routh array, there are certain assumptions or certain necessary conditions which everyone should follow. Number one, the coefficient of all the terms which are appearing in the characteristic equation, all the terms appearing in the polynomial form of the characteristic equation, they should be positive in nature. They all should be positive in nature. It doesn't work that if single plant is working in the system. It should work for all the systems. Now how to calculate b1 b2? Let's see. For b1, remember this thing, we're gonna start the layer which is just back, that is from b1 we have a1. Now a1 will get multiplied by a2 minus the other way, 19 to 93, divide by a1, that is b1. For b2, we'll start with a1 only, it gets multiplied by a4. So a1 a4 minus the other way, a3 a2 upon 1 minus a3, and then so on. So this is how you can prepare the complete array, and the number of rows will be 1 plus the highest power of s. Now how much is the highest power of s? 7. So we'll have 7 different seven different these arrays in which these parameters b1, b2, c1, c2, d1, d2, e1, e2 and f1, f2 are to be calculated. Clear? Now let me take an example over here, then you will be able to understand how the things are to be done. Let me take a very simple example over here, and then we'll discuss the drawbacks of this. Now suppose I have a polynomial equation. It's an example. Suppose I have a polynomial equation which is ps equal to s4 plus 2 to s cube plus 164 s square plus 458 s plus 315. Suppose I have this polynomial equation. I need to prepare the Routh array for this. Let's say prepare a Routh array for this system. Now we're gonna first note it down the highest powers of s. Now suppose if any power is missing, we'll replace it by 0 factor. So s4, s cube, s square, s and a blank constant, so all the terms are there. Now array, first entry, it starts with the first coefficient, that is 1, and leave the another, move to another 164, leave the other, move to next, that is 315. Second, we're gonna write down the missing ones. So missing ones are 225 and 405. Clear? We have these elements with us. It's not 225, it's 25. Sorry, my mistake. It's 25 over here. 22. Third, now the highest power of array is 4. So number of arrays will be n plus 1. So 4 plus 1, 5. So this is 4, this is 5. It should be finished by 5th row. Now third entry, what we do is we multiply 22 into 164 minus 1 into 408, that is 408, divide by 22. So that will be entry number 1 in third row. So it comes out to be 143.18. Second entry. So we're going to multiply 22 with 305, subtract 408, and then we can write down the next one. So the next comes out to be 315. Fourth. Now for fourth, this number which we have 143 gets multiplied by 108, 1 gets multiplied by 315 and divide by 14318. So we have C2 which comes out to be 409.6, and then the next one, so we'll have this into this minus this into this. If nothing is there, treat it to be 1 until unless told. So this will be 409 into 305 minus 318, 143.8, divide by 409, so it comes out to be 350. Now the important thing about Routh test. Now look at the entries in all the, now the row is completed. Number 1, remember this thing. First we need to finish up the row. Now row is finished. Number 2. Now once the row is finished, take a look at the signs of all the entries which are there in the first rows. All these numbers, they are positive in nature, they have positive this thing. So that means system is stable. For system to be stable, remember this, for the system to be stable, for the Routh array, the first entries in all the columns should be positive. So this is how we test Routh array. Now there is only one drawback to this thing. No doubt it tells us the stability. It tells us the stability of the system, but it does not tell us about the exact location of the system. Exact location it doesn't tell, it just give you the idea. All the entries are positive, stable. If any entry is negative, the system is negative. Clear? So this is all about the Routh test. I hope if you have in the next lecture we'll continue with the Routh array. We'll prepare more problems, we'll solve more numericals. So by the time we reach towards the next topic, you should be familiar with stability and Routh test. Thank you.